So before we get started, are there any questions about stuff from last week or previous weeks? You have questions about? Comments, concerns? So I was talking a little bit about this with Abby and Nicole, but what's really great about multinomial regression is that I think it's a pretty straightforward kind of extension of logistic regression. So I don't think that there's going to be a lot of new concepts or terms introduced today that you don't already know. But hopefully I'll convince you that it's a pretty straightforward, pretty straightforward generalization. So as always, if you want to follow along, you can download the Cordo document by clicking here and then opening it up in our studio. So last week we talked about ordered response categories. So they have some inherent ordering to them, right? And I introduced the proportional odds model or the cumulative logit model. So this week we're going to be talking about unordered response categories. So these are categories that have no really inherent order. But you might be able to impose some order, like in Nicole's example, and then also the example that we're going to talk about later. But generally, there's really no ordering to them. So how do we analyze that data? So what I want to do is I want to introduce the multinomial logistic regression. So I want to talk a little bit about the basics of it. So I want to introduce the multinomial distribution. And then I also want to talk about the relationship between logistic, ordinal, and multinomial regression. So how are they the same? How are they different? And then I want to couch this within an example. So I want to walk through how we perform multinomial logistic regression on a data set that has unordered categories. So that is the agenda for today. So as I've kind of emphasized over the past few weeks, it's important that we adequately model the data generating process, right? So what do we need? We need a distribution family that describes the outcome variable reasonably well. So when we talked about logistic regression, we talked about two distributions. We talked about the Bernoulli distribution and we talked about the binomial distribution. So the Bernoulli distribution has an N of 1, right? So there's only one event, one trial, and there's two possible outcomes. So you can get success, failure, 0, 1, heads, tails, whatever your two options are, right? So within the Bernoulli distribution, there's only one parameter, and that's P. So the binomial distribution is an extension of the Bernoulli distribution, where within the binomial distribution, we have a fixed number of trials and a whole bunch of independent Bernoulli events with two possible outcomes, right? So success, failure, 0, 1, etc. So what do we do when we have more than two outcomes? So this is the case that we're presented with when we talk about multinomial regression, where we have more than two outcome variables or more than two outcome responses. So what do we do then? Well, luckily what we can do is we can actually just generalize the binomial distribution to multiple response categories. So if you have more than two outcomes and a fixed number of trials, we just fit what's called a multinomial distribution. And really what's important here is, again, it's just an extension of the binomial distribution. So this is the probability mass function here, the equation, where we can get the probability of certain outcomes. And that's a function of the number of trials you have, the number of times that event occurs, and the probability of occurrence. What's important here is that we can extract the mean of that particular response category. And that's just n times the probability of that event occurring. And then the variance is just n times the probability of that outcome occurring times 1 minus p sub I. And then to get the standard deviation, we could just take the square root of that. What's important here is, again, we're using the multinomial distribution, which is an extension of the binomial distribution. And that's essentially what we're going to be using to model these multinomial categories where we have more than two outcomes here. So now let's compare multinomial logistic regression to things like ordinal regression. So what are the similarities? What are the differences? So last week I proposed the ordinal regression and I presented the series of equations. So in ordinal regression, we're fitting J minus 1 equations simultaneously, right? J refers to the number of response categories. So if we have 4 response categories, we're fitting 3 equations simultaneously, right? And in each equation, we're estimating a different intercept value denoted by alpha. And then alpha sub 1 is for the first equation, alpha sub 2 is for the second equation, and so forth and so on. Does anyone remember what alpha refers to in these equations? Anyone? Ham, did you say something? What? Yes, the intercept. But what does the intercept represent? How is it interpreted? Like, what does the alpha values represent in an ordinal regression?
Predictors are all 0, and what's the base log off?
So it has to do with the log odds, right? But what type of distribution do we usually use for ordinal regression? So do you remember the distribution family that we use in ordinal regression? No, anyone want to help him out? Alex, dude. Seems like you know. Yeah, so it's the cumulative probability. So in each equation, the intercept or the alpha value here represents the cumulative probability of being in a response or below it. So that's what we're estimating in each equation, right? So we have a different alpha. And this is also referred to as a threshold or cut point in that continuous distribution, right? So within ordinal regression, we have a constant slope. So we basically fit the same slope across all equations. So we're not estimating different slopes. So this is related to the proportional odds assumption of ordinal regression, or at least the proportional odds model, right? So we're not estimating different slopes. And then we also have this weird subtraction thing going on here to make our interpretation a little bit more intuitive here. So that's the ordinal regression. What about multinomial regression? So similarly to ordinal regression, we fit J-1 equations simultaneously, but in each equation, we're comparing a particular response category to a baseline, right? So that's key, that's critical. That's one of the main differences between multinomial regression and an ordinal regression. Each category is compared to a baseline or reference condition. And then we also see here the slopes are not constant, so that is not an assumption of multinomial regression, right? So we can estimate different slope coefficients in each model. And also we get our addition back, yay. So it's a little bit more relatable to regression. So those are the main similarities and differences between multinomial regression and ordinal regression. So the key feature of multinomial regression is that we're comparing this response category to a baseline category or reference category. So in logistic regression, right, we usually label something as 0 or we label something as 1. So in this context, let's say that our baseline category is 0, right? We're going to label that as 0. If that's the case, the probability that y equals 0 is going to be p sub I 0. And the probability that it's another response category is going to be 1, right? So if that's the case, then the probability that y equals 1 is going to be p sub I 1. And what we can do is we can fit a model that's very similar, if not the exact same, as a logistic regression, where we're going to use the logit link function here, and we're going to model the log odds. So here we're going to model the log odds that you're in one particular category versus the baseline category, this p sub I 0, right? And we're going to model that as a linear function of the predictors. And similarly to logistic regression, the interpretation is the exact same. So our slope coefficient can be interpreted as when x increases by 1 unit, the odds of y equals 1 versus baseline is expected to multiply by a factor by taking the exponent of the beta. And the intercept is when x equals 0, the odds of y is expected to be the exponent of beta. So the interpretation is the exact same as it would be for logistic regression. Again, we're fitting multiple equations and we're comparing a baseline to a reference category. To make this a little concrete, I conducted a study in 2018 that looked at the study habits of college students. So we asked them a whole bunch of questions about their study habits, and we performed a whole bunch of multinomial regression models. And this is one example from that paper. So we asked students, which of the following best describes your pattern of study? So do you engage in light cramming? So this would be that you study maybe the day before an exam, right? So all of your studying occurs the day before. Do you engage in heavy cramming? So an example of this would be that you study, several hours before the exam. I don't recommend that you do that, but some people do that. Or do you space out your study? So is your study spaced out over days and weeks before an exam? In this particular example, we use space as our baseline category. And what we did is we just fit 2 equations, right? So there's 3 response categories. We fit 2 equations, right? J-1. And in the first model, we looked at the log that individuals engage in light cramming versus spacing. And then in the second equation, we just looked at the log that individuals engage in heavy cramming versus spacing as a function of the predictors. So this is kind of more of a concrete example of essentially the types of models that we're fitting in multinomial logistic regression. And something that I want, yeah, Ham?
How is it different from just doing two logistic regressions? Compare like one just light versus space outcomes.
So like that's related to what Nicole was talking about in terms of like the stratified sample, right? Where you're just performing multiple logistic regressions. Here we're fitting all these equations simultaneously. And I think that there's more nuance in this type of approach where if you fit in the multinomial regression, you're kind of throwing out data, right? Because you're looking at two particular categories versus, 4 categories or 5 categories. But I mean, you could maybe do that way, right? Where you're just performing just regular logistic regressions, but this is all within one model, right? Where you're not performing multiple actual logistic regressions. It's all in one model, which is preferable.
And the results will be different. Like at least quantitatively different.
They should be pretty similar. You should probably get similar results. The benefit of this multinomial approach, though, is that you can just have all the categories and compare each one to the baseline, right? Whereas you can't really do that if you're performing separate logistic regressions, right? Because you're actually throwing out some of the categories, right? Because that nuance is not preserved in a logistic regression. If that makes sense.
The result is also interpreted as like compared to the baseline.
Yeah, it's to pay the baseline. But like if we were going to run just a regular logistic regression, we would have to basically code our data in a way that we're losing some of the categories, right? Because we can only have space versus light, right? So what do we do with heavy cramming? Do we remove that, or do we like include that in with light cramming? I mean, we could probably just have cram versus space, so you could do something like that. But I think it loses some of the nuance to do it like that. But it could be reasonable to do something like that. This is just a way to capture all of the categories and compare them to a reference category.
Also, I'm not sure I understand like how do we decide whether we should treat it multinomial? Because it sounds like this question is like how heavily you cram for it.
Yeah.
But in that sense, it seems ordinal.
Yeah, no, that was a question that I was asking to Nicole, right? So like the example that we're going to use later on, again, you could probably treat it as ordinal if you wanted to. But again, I think also it might be theoretical, right? You might have a particular reference category or baseline category that you want to compare all the other categories to, whereas in ordinal, you can't really do that, right? You're getting a cumulative probability. But again, I think that'd be more theoretical, right? To decide if it's going to be ordinal or if it's unordered. So like I guess a clearer example would be this, where you have different parties, right? Political parties, which are not ordered, right? And also, I don't know if I would order, I guess you could order this, but I don't know if there's like an inherent order to heavy cramming and spacing. Yeah, I don't know. I guess you could label it like 1, 2, 3, but I think it'd be theoretical. One thing that I wanted to mention here too, that the choice of your baseline category should be theoretically motivated. So by default, what R will do is we'll just put the first category that comes alphabetically as your reference, and that might not be something you're theoretically interested in. So this should obviously be thought of like a priori, instead of just choosing whatever reference category that it gives you by default. So that's something to think about as well. So just kind of as a summary with multinomial regression, we're fitting J-1 equations, right? Where each category is compared to a reference or baseline. And what we can do with each of the fitted logits is that we can actually take those logits and we can do other comparisons, as Nicole talked about in her presentation. I just prefer to re-level instead of doing the subtraction on the logits themselves, but you can definitely take those logits and you can calculate whatever comparisons you want, if that's what you're interested in. All right, so that is kind of an introduction to multinomial regression. Are there any questions, comments, confusions? I'm hoping you guys see the kind of extension from logistic regression to multinomial regression. So again, I don't think that's too far stretch. I think it's pretty near transfer. But if there's any confusion, please let me know. So what I want to do for the rest of class is I want to walk through a data set and apply multinomial logistic regression to that data set. So the data set that we're going to use is from the NHANES survey, which is the National Health and Nutrition Examination Survey. And this is a data set that you guys looked at when you did the missing data lab, and we're going to use it again. So I did want to use the data from my paper in 2018, but unfortunately I could not get access to the raw data to use that. I won't say why, something to do with the PI, but we're going to use this data set. I think it's a pretty good data set for demonstrative purposes. So this data set is pretty massive. There's about 75 variables, and the goal of this particular data set or the survey is to assess the health and nutritional status of adults and children. So again, as I said, there's lots of variables in this data set. It's very rich, but we're only going to look at several variables from this data set. And at least for the first part of class, we're going to try to answer this question. So can we use a person's age and whether they engage in physical activity to predict their self-reported health rating? So for the first part, I want to look at three variables. So there's this health gen variable in the data set, and this is self-reported rating of health. So there's 5 categories here. So excellent, very good, good, fair, and poor. And again, we could probably order these, right? From least to greatest, right? In terms of health, but we're going to model these as unordered. We're going to look at age. So this is age at time of screening. And then we're also going to look at this phys active variable, which basically asks if individuals engage in physical activity. If they do, they say yes. If not, no. So those are 3 variables that we're going to look at to try to answer this question. So first, let's go ahead and clean up the data set a little bit. So what I'm doing here is I'm removing anyone that's under the age of 18, and then I'm only selecting 4 variables. This education variable we're going to look at later, but for now, we're going to look at the health gen, age, and physical active. And then we're going to drop NAs. We're not going to deal with the NAs. So we can go ahead and run this code. Not going to deal with that right now. So we can see here that health gen is a factor, right? We have those 5 categories. Education is also a factor that we're going to look at later. Age is an integer in the data set. And then physical active is also a factor, so no and yes. So let's go ahead and just take a look at our data. So on the left-hand side here, what I have is just a bar plot. I'm looking at self-reported rating, and we see in our data set, at least for the majority of folks, they report good health. We could look at the histogram of age, and we can see that there's kind of a nice distribution of age in the data set. And then when we look at the bar graph for whether individuals engage in physical activity or not, we see that for the majority of folks, they say that they engage in physical activity in this data set. We can also look at age and physical activity by health rating. When we look at age as a function of health rating, what we see here is that for older individuals, they're more likely to report poor health. And there doesn't seem to be too many differences between the other categories here. They're pretty overlapping here. The medians are pretty close to one another. When we look at physical activity as a function of health rating, what we can see is that individuals who say they engage in physical activity are more likely to report very good to excellent health, which makes sense. And individuals that don't engage in physical activity are more likely to report poor or fair health, which I think makes sense. So let's actually see if physical activity and age can predict health ratings here. So we're going to fit a multinomial regression model here. And we're going to use the multinom function, and that's part of the NNet package. So if you have that installed, you should be able to run the multinom regression function here. So let's go ahead and run that model. And see, the setup of this particular model is pretty straightforward, very comparable to what we've been doing with our other models, where we're looking at health gen, which is going to be our unordered category, and then as a function of physical active and age here. So let's just go ahead and run that. So the output is actually atypical to what we're used to when we're running regular GLMs or LMs here. So I kind of wanted to walk through a little bit the output here. So this is just the actual fitting that's done, the maximum likelihood or whatever estimation algorithm is being used here. So if it converged or not. The coefficients and standard errors are separated out here. And what you'll notice is that it's not in long format now, but it's in wide format. So what we have here is each row is going to be a particular model that we're fitting. So here we have 5 response categories. We're fitting 4 models, and each row is a different model. So the first row is going to be very good compared to excellent. And then we have our model, right? Our intercept, and then our coefficients for the physical active variable, and then age. And then the second row looks at good versus excellent. The third model looks at fair versus excellent, and poor versus excellent here. And we know which one the baseline category is because it's not represented here. So we know that it's excellent. And in R, by default, it goes with whatever's first alphabetically, which is excellent here. So each row is a particular model. And then the standard errors are also separated out. And there's also something else missing here. Do you guys notice what's missing from this output? So it just ends right here. So this is the maximum likelihood and our deviance. Yeah, p-values, right? We need p-values. So where the heck is the p-values here? So to make that a little easier, we can use something like tidy from the Broom package, or we can use this model parameters function from EasyStats. I like using model parameters. But when we run this, we actually get our p-values and we get an output that is more familiar to us, that we're used to. So we can go ahead and run this. And then let's look at the output. So we get output that looks like this. So when we run the model parameters, we can just put in our model here, and then exponentiate is equal to false here. So these are going to be our log odds. That's what the coefficients represent. And what I'm doing here is I'm filtering out. So we're only looking at one model, and we're looking at the fair versus excellent model. So that's the model that we're going to look at, and that's the model that we're going to interpret for at least the first part. We can also exponentiate these coefficients and get the odds ratios. So within model parameters, we can just set the exponentiate to true. And when we run that, we get our lovely odds ratios here. It's kind of cut off here, but you can run this in your console in RStudio and get the actual odds ratios here. So this is a nice way to get the kind of summary output in an interpretable format. So let's go ahead and let's look at the model comparing fair versus excellent. So this is the actual model equation, looking at the log odds of reporting fair health versus excellent health, right? So we have our intercept, we have our age slope, and then also the physical active slope here. So let's go ahead and interpret each of these coefficients in the context of the model. So let's first look at the age coefficient. So this is the slope, and it is 0.001. So is this particular coefficient statistically significant? It is not statistically significant, right? But we're still going to interpret it anyways, just for fun. So how we can interpret this particular coefficient is that for each additional year in age, the odds a person rates themselves as having fair versus excellent health are expected to multiply by 1.001, holding physical activity constant. So a different way we can interpret this is as age increases, you're more likely to report fair versus excellent health. So that's how we can interpret that coefficient. What about this physical active coefficient, which is negative 1.66? How do we interpret that? So we can say the odds a person who does physical activity will rate themselves as having fair versus excellent health are expected to be 0.19. So this is the exponent of negative 1.66 times the odds for a person who doesn't do physical activity holding age constant. So because this particular coefficient is negative, that means that the odds that you're in the baseline condition is more probable than being in the other response category. So we can say that a person who does physical activity is more likely to rate themselves an excellent versus fair health. So that's how we can interpret that particular coefficient. And then we have our intercept value of 1.03. So this is the odds a zero-year-old person who doesn't do physical activity rates themselves as having fair versus excellent health. And those odds are about 2.801, right? So two times more likely to report fair versus excellent health. which I think makes sense. But it's also important to note that we did not mean center age here, right? So a 0-year-old person doesn't really make sense in this context. So we probably want to mean center that age variable to make the intercept a bit more interpretable. So this is how we can interpret those coefficients for the fair versus excellent model. Again, pretty straightforward, right? From going from logistic regression to ordinal regression to multinomial regression. I think a very straightforward generalization. So now what I want you guys to do is I want you to run a model that looks at the good versus excellent condition. So the good response category versus the excellent response category. So I want you to run these models, and I want you to take a couple minutes, and I want you to interpret those coefficients. And then we'll go through the interpretation of each of those coefficients. You should be able to run this all from the browser. You can actually run this from your iPad too. It runs, it runs in the browser, so you can follow along. Yeah. All right, so let's go through this model looking at good versus excellent health, right? So this is the model equation. So let's go through the actual coefficients here. So how do we interpret the age coefficient? So first off, is it statistically significant? No, but we're still going to interpret it anyway. So who wants to interpret this coefficient?
For each additional year of age, and the log odds of being good as opposed to excellent decrease by 0.003.
Yep. And then we could also talk about this in terms of odds ratio, right? So we can just take the exponent of that. So for each additional year in age, the odds a person rates themselves as having good versus excellent health are expected to multiply by 0.997, holding physical activity constant. So as age increases, I shouldn't say higher probability, higher odds to report excellent health versus good health. We don't want to talk about this in terms of strict probability because it's the odds. So I'll have to change that, but yes. So thank you, Nicole. All right, what about physical active? How do we interpret that particular coefficient? Yep. Would it be a decrease, an increase, decrease? Yeah. So we can also talk about this in terms of odds ratios, right? So we can take the exponent of negative 1.01. So we can interpret this as an odds a person who does physical activity will rate themselves as having good versus excellent health. And it's expected to be 0.364 times the odds for a person who doesn't do physical activity, holding age constant. So essentially a person who does physical activity are more likely to rate themselves in excellent versus good health, right? So we always want to pay attention to the actual sign of the log odds, right? And that will determine if they're more likely to be in the baseline category versus the other category. And who wants to take a shot at interpreting the intercept value? It's essentially the same interpretation as the other model. So what does the intercept represent in this case? The log odds for
being in the good category for excellent,
Yep.
holding age at its mean center, right?
So it's not mean centered.
Age is 0.
Yep.
And physical activity, part of it's the grand mean.
So this is just dummy coding. So it would ever be first alphabetically. So it'd be like the no, so no engaging in no physical activity. That's right, Alex. Right. So the odds of 0-year-old person who doesn't do physical activity rates themselves as having good health versus excellent health are 7 times more likely than those who do engage in physical activity. So those reporting no physical activity are more likely to report good versus excellent health here. And then again, we should probably mean center age here to make the intercept a little bit more interpretable here. But this is how we can interpret the coefficients in a multinomial logistic regression. And we could do that for each of our models, right? We'd have to go and interpret them. So as I kind of talked a little bit about before, the baseline is important within multinomial logistic regression, but it should be something that's theoretically motivated and guided. So you should choose your baseline reference wisely. Here, we just chose whatever came first, alphabetically, right? We let R choose our baseline or reference condition, but we might have a particular baseline or reference that we want to use here, right? So what I've shown here is how we can re-level our variable to change the baseline. So we might want to reference everything to the poor condition, right? So this is how you can go about changing the baseline or reference for the model by just changing the reference to poor instead of excellent. And then we would rerun our models, comparing everything to the poor category. So what I've walked through is how we can interpret the summary output. And in very simplified models, go ahead and do that, right? Where we don't have any interactions, we have 2 levels to a factor, go ahead and interpret the summary output. However, things become a lot more difficult when we have lots of predictor variables, lots of categorical predictor variables with multiple levels. And then when we get into interactions, the summary output is very hard to interpret. So my suggestion is to report the likelihood ratio test for the model. And we can do that using the ANOVA function. And we get something that looks like this, where we have our likelihood ratio chi-square statistic. And we can interpret this as kind of main effects. If we have an interaction, we can interpret it as main effects and interaction. It makes our life super simple. And that's one thing that I saw in some of the labs, especially the logistic lab, where we had multiple political affiliations, right? There was like 6 categories. If you interpret the summary output, everything is in reference to the baseline, right? we want to look at all the possible pairwise comparisons, right? We want to see what differs from one another. And the summary output doesn't give us a complete picture, a whole picture of that. So I think that this approach is a little simpler and more straightforward than trying to figure out what the summary coefficients mean. So I wanted to walk through how we can, extract the information that we need to make those comparisons. But here we see that overall physical activity is statistically significant and age is statistically significant. So what we would then do is we'd follow this up with our pairwise comparisons. So what I'm highlighting here is the M-means approach. So I have been trying to incorporate marginal effects or the marginal effects package over the past few weeks because I think it's pretty straightforward and easy for people to use. However, there are some kinks with trying to use marginal effects with a multinomial model. And I'm working with the creator of the marginal effects package to, make this a little bit more intuitive. So hopefully in the next week or so, I'll also have marginal effects code here that you can run it on, but there's some issues with it. But M-means works pretty well to extract the information that we need. So if we have a significant main effect of physical active, what we want to do is we want to follow that up and look at the pairwise comparisons, right? So we want to extract the log odds for the difference between the variables. Now, in this simple context, we can look at the summary output and we can get those log odds, right? But this is a way that we can get the log odds for those differences. And this will become really handy when we're dealing with categorical predictors that have more than 2 levels, because we can get all the pairwise comparisons for those levels. But what I want to do is walk through kind of the output. So it's not very straightforward, unfortunately, but this code will get us what we need. So what I wanted to do is kind of walk through each line here and kind of talk about what it's doing and what we're getting here. So we can use the M-means function and fit our multinomial model that we fit. And then what we want to do is we want to look at the interaction between physical active and health gen, right? So we want to look at each rating as a function of physical active here. So that's what this particular line is doing. So let's go ahead and just run this and see what it looks like. So what we get here is for each level of our dependent variable, right? So each response category, we get the probability or the predicted probability that they engage in physical activity or they don't engage in physical activity, right? So if they engage in physical activity, what's the probability that they say that they're excellent? If they don't engage in physical activity, what's the probability that they will rate themselves as excellent? So that's what we get here, but we get probability. So that's what by default M-means will give us is probability, but we don't want probability. We want log. We want the log. So we need to do another step to get this information in log form. So what we can do here is we can use this contrast function. And within this contrast function, I'm using this regrid function. So what this will do is it will back transform the probabilities to the log scale, which is what we want to mimic our summary output here. So that's what this regrid is doing, is basically back transforming probabilities to logs. Then there's this treatment versus control 1 argument that I'm setting here. This will ensure that each response category is compared to a baseline or reference, right? So we need to make sure that we're taking good and comparing it to excellent, fair to excellent, very good to excellent, and so forth and so on. So that's what setting this treatment versus control 1 argument does. And then we're going to look at the difference between each of the response categories. So fair versus good, good versus excellent, etc., by physical active. So let's go ahead and just look at what that looks like. So now what we see here is that we have physical active equals no and physical active equals yes. And then we have this contrast here. So very good minus excellent, good minus excellent. These estimates are the log odds. So important feature of logarithms is that if you subtract them, you're actually getting the log of the odds between those two conditions, which is kind of neat here. So these are our log odds for the very good compared to excellent condition when you say you don't engage in physical activity. So we get all of our log odds here. Then what we can do here is we could actually just take these and subtract them from one another to get the difference between yes and no, right? That difference that we're interested in, but we're just gonna let m-means do that for us. So what we can do is we can call the contrast function again. And what we're gonna do is we're actually going to take the difference between yes and no now as a function of the log odds between very good and excellent here. That's what this line of code is doing here. So let's look at what that looks like. So now what we have here are log odds for the difference between yes and no. These estimates are the same estimates, excuse me. Sorry. So these estimates are the same estimates that we'll get from the summary output. So we can look at the summary output and these are the exact same, right? This is just, I mean, I guess it's kind of a little bit more convoluted way to get those log odds, but this will become really handy when we have lots of levels for our categorical predictor, right? This is kind of overkill now. There's lots of steps to this, but again, we can get our estimates for each model in a kind of a nice succinct way, and we can also get our p-values this way, right? So we can see here for each model, the estimate is negative in each case, right? So if you engage in physical activity, you're more likely to rate yourself as excellent versus very good. Another thing I wanted to mention here is that there's this rev pairwise argument I'm setting here. That just determines the subtraction. Does it go yes minus no or no minus yes? The reason why I set this rev pairwise function is to make it more comparable to the summary output. You could change this, just make sure you know which direction the subtraction is going, right? When you're interpreting the estimates here. But so this is, I guess, kind of a maybe not intuitive way to get the log odds for this particular comparison. But this is probably the approach that I would use. This is just kind of a nicer version of what I just did right here. This is just outputting as a table the difference in log odds between yes and no for our very good, excellent, or good, excellent comparisons. So m-means uses something called the marginal effects at the mean. So we can't just plug in age and get the actual average effects, unfortunately. So we can use marginal effects though to get our log odds. And what we can do is we can use the average slopes function, which we've used before. So again, I think that this particular syntax is more straightforward than the syntax from m-means. And again, I'm working with the creator of the marginal effects package to make this work. So it works in very simplified contexts, but there's some kinks that we need to figure out and work out. One of those kinks is that this hypothesis argument here is set to reference. So it's going to compare each category response to a baseline, right? But it doesn't preserve the baseline that you set in the model itself. It just uses whatever comes first alphabetically, which is problematic. In our case, right, we're just using excellent, but if we set it to poor, it doesn't observe that, unfortunately. So we need to make some changes here. We could change this to just pairwise hypothesis, and then we could just extract the actual estimate itself. But again, these estimates are the same as the summary output. But this is just a different way to extract that information. So let's talk a little bit about predicted probabilities. So we can use our ggm-means function to get the predicted probabilities for our physical active condition, right? So we could get the predicted probabilities for each response, right? Excellent, very good, good, fair, and poor. And then we can use this and we can create our figures from the ggm-means function. Here, I'm just highlighting this as a stacked bar plot for a categorical predictor, right? Where in each bar we have the probability or the predicted probability. This is one way that we can visualize this type of data. This is a stacked area plot using ggplot. So this is using ggpredict and then feeding that into ggplot. I kind of like the stacked area plots that we see here. I probably would change this up a little bit and take the actual responses and put them in the actual shaded areas, but that's for another time. But we can kind of see here that there's not really much going on, right? There is something going on in this poor condition here, where as you get older, right, you're more likely to say that you're in poor condition. But for the other conditions, there doesn't seem to be too much going on here. But this is one way that we can visualize a continuous predictor in this context. All right, so now I want to talk a little bit about model selection. So let's go ahead and make the model a little bit more complicated. So now let's add education to our model. So education takes 5 levels. So there's 8th grade, 9th and 11th grade, high school, some college, and college grad. So now let's go ahead and just compare a model where we just have age and physical active, and compare that to a model that has age, physical active, and education to it. And similar to what we've done before, we're interested in comparing the null hypothesis that there's no difference between those conditions to the alternative hypothesis where there is some significant effect. And what I'm doing here is I'm fitting 2 models here. So I'm fitting a multinomial model that's reduced that doesn't have education, and then there's a full model that has education added into it. So what we can do is we can use our ANOVA function and we can compare these 2 models to one another. And what we see here is that the model that has education in it seems to fit significantly better than the model that doesn't have education in it, right? So our chi-square is statistically significant. So what we can infer from this is that we should be running a model that has education in it. It seems to be a better model. So again, we've already done this type of stuff before with our ordinal regression, our logistic regression, our multi-level modeling. So nothing new here, but this is one way that we could do model comparisons. Again, we could run the model and interpret the summary output, but I prefer the likelihood ratio test approach better. So we can use the ANOVA function and we can report main effects here. So here we see that there's a main effect of age, there's a main effect of physical active, and then there is a main effect of education, right, for our model. So now we need to follow this up, and we can use the m-means functions that I talked about earlier to extract the log odds for the comparisons of interest. So do you now see why something like this is really great? Do you see all the pairwise comparisons that we're doing here, right? So this gives us everything that we need to report in a paper. If we just looked at the summary output, we would have to re-reference to get all of these comparisons, right? So we run our summary output for our model. Everything isn't compared to what the reference category is. So it might be 8th grade compared to 9th, compared to high school, compared to some college grad. That's all we get. So then we would have to re-reference and then get the log odds for those comparisons. I think that's just burdensome. This, again, not that intuitive, you know, a couple lines of code, but we can get all the things that we need to report. So now here we get all of our differences between each of our contrasts, right? So the difference between 9th and 11th grade minus 8th grade for the very good, excellent model, right? So this is the stuff that we want to report. And then we can take the GG means and then feed it into ggplot and create a stacked bar plot with the predicted probabilities in each of the bars. So that's one way that we can visualize the categorical variable of education. All right. So are there any questions so far about visualizations, interpretation, model comparisons? I'm hoping it's fairly straightforward. So we'll see on Wednesday how straightforward it is, but I have faith. So the assumptions that underlie logistic regression also underlie multinomial regression. But the way that we can test assumptions of multinomial regression is not really straightforward. I don't think there's really a good alternative to this. But essentially what we're going to have to do to check for things like linearity and outliers and multicollinearity is to basically fit separate logistic models for each of our categories. So that's what I'm highlighting here, where we have the excellent factor, where if it's excellent, you just get a 1 and everything else gets a 0. And then we do the same thing for very good, good, fair, and poor. And then we fit separate logistic models for each of those categories. And then we can run check model on each of them. And we can look at things like linearity, right? So look at our binned residual plots. And then we can also look at outliers and multicollinearity. So I don't know of a good alternative. Nicole, maybe since you do multinomial models more, I don't know if lots of people don't really check for assumptions. It can't be helpful here. So this is one way to go about it. Again, like you can't just throw this multinomial model into check model, it won't run, unfortunately. So this is one way that we can get, or at least check the assumptions for our model. So we can look at model fit using McFadden's R-squared, or there's a whole host of different R-squared measures that we can use. Again, we've been using the McFadden one, but again, there's a whole host of them. So this is just the code to get that. So similar before. So when we're reporting multinomial regressions, when we're reporting ordinal regressions and logistic regressions, the odds ratio serves as our effect size measure, right? That's what we usually report as our effect size. So the 2018 paper that I wrote, one of the reviewers recommended that we transform our odds ratios into Cohen's d. So you can take your odds ratio and make it into maybe a little bit more interpretable measure, Cohen's d. Everyone knows that. So what I have here is the equation to take our odds ratio and converting it into d. And the effect size package from EasyStats also has this function called odds ratio to d, where you just throw in the odds ratio and it gives you the Cohen's d value for it. So this is an alternative. So if you want to don't want to report odds ratios and instead you want to report Cohen's d, maybe your advisor is more familiar with Cohen's d. This is one way that you can do that. So instead of reporting odds ratios, you can just transform that into Cohen's d. So now I want to talk a little bit about writing up the results. So as I stated here, you could interpret the summary output, but if you have more complicated models, I don't think that you should resort to making the interpretations from the summary output. So instead, just report chi-square test, right? So say you have a main effect of age, you have a main effect of physical active, and then main effect of education, report your model fit. And then what you want to do is you want to follow up those effects and report the log odds for each variable of interest in the J-1 models, right? So we look at each model. Yeah, Alex? So we could probably use ordinal here. Again, it's theoretical, right? If there's maybe a way that you can imagine this as being ordinal, right? Going from like least to greatest. Yeah. So like this, so yeah, we have excellent, very good, good, fair, poor. We could probably, rate this as 1, 2, 3, 4, 5, right? Yeah. Yep. Again, we're just treating this as unordered. It's very possible that you can put these as ordered, right? And I think that might simplify things a little bit too, because then you have just the continuous variable, right? The logit and the cumulative probabilities, and you don't have to do all of this stuff, but just for demonstrative purposes, we're just treating this as unordered. So again, as I stated here, when we follow up our main effects, we want to report the log odds for each variable of interest in each of our equations, right? So the very good versus excellent, what's the difference between physical activity? What's the difference between education? What are those significant differences? We also want to probably include tables with our results. So I don't know if figures are reasonable in this context, right? Because we're looking at the log odds of one category versus the other category. So it might be helpful to actually visualize the predicted probabilities in each category. But for the actual results themselves, I think a table might be better with odds ratios. So I have an example of that in the next slide. So this is just taken from one of my papers where we have multiple questions that are multinomial in nature, right? But what we have here is the frequency of the response, right? So what's the percentage of people that said longest, interesting, worst in, or light cram versus heavy cram? And then we have the odds ratio for each of our predictors of interest, right? So this represents the log odds of being in one category versus the other category. I don't know if it would make much sense to kind of visualize this as predicted probabilities, right? Because we're comparing categories to one another, but predicted probabilities might be something that you want to use or your reviewer wants you to use. But in this context, I think maybe tables are better to visualize the results. Nicole and I were talking about this before her presentation. Is this how you usually report your results in a table? I do like your visualization that you had though, looking at the log odds. So that would be a good visualization too. But
Yeah, I prefer it.
yeah, because again, with the predicted probabilities, right? That's not what the models are actually looking at, right? We're looking at the log odds between these two conditions, whereas the predicted probabilities are just looking at the probability in each category. Again, you can visualize the comparison between those two, but that's not what the actual model is representing. So there's different ways that you can highlight these things. So lastly, what I wanted to just briefly mention is that, again, this is a very simplified context, right? But we can extend these things to multi-level models. So we can perform multi-level multinomial models. There's a couple packages that I know of that we can that can do multi-level multinomial regression. One is the BRMS package that we used on Wednesday or last Wednesday, and the package we're going to use when we start talking about Bayesian regression. So that can easily be extended to multi-level multinomial regression using the BRM function here. There's also this MC logit function that can do random effects. I haven't really played around with that much, but that is one package. And I don't know if there's any other packages that folks use. Do you do multi-level multinomial stuff? Oh, okay. So these are kind of two packages that we can use to model the multi-level nature of our data, if we have it.
If you
Yeah.
want to be a part-time DJ, that should be.
MC Logit, yes. I love the names that people give to packages. They're so creative and unique. Love it. So yeah, so that is all that I have for multinomial regression. On Wednesday, we're going to work through a data set. And I've tried really hard to make the labs more manageable to where you can finish them in class. So I'm hoping that Wednesday, you guys will be able to at least get most of it done in class. There is going to be a large writing component, but that's pretty much going to be the brunt of the lab. It's just writing up these results. So that's about it. So yeah, if you guys don't have any questions, you guys are free to go.